Okay, so our first question for today is why do we do LU factorization? We'll talk about that briefly. Next, we are going to go and actually put LU factorization to use, and that would be solving a linear equation like AX equal to B using LU factorization. These two topics are actually tied to each other. And the third one we are going to deal with is what will happen if we have permutation during the LU factorization. So the question is what to do if permutations are involved during Gaussian elimination. Okay, item 1. Why do we do this? LU factorization, the steps are exact copies of what we did in the forward elimination step of Gaussian elimination. So we are just keeping a record of what we are doing. Those multipliers that show up are used are stored in L. The matrix U is the upper triangular matrix that is left at the end of the Gaussian elimination. And it looks like on the first side that it is nothing other than just some bookkeeping. Bookkeeping itself is not bad, but beyond that, what do you do with this? What happens is in most engineering situations, you have an instrument or an object that is being put through a variety of tests. It's like having a bridge. Depending on how much load you put on this and where the load happens to be, the amount of stress on different components of the bridge are going to be different. Suppose you want to find out how much stress is going to be on each component of the bridge. This is truss here or this truss over there. Well, finding that information is like solving a linear equation. And the question is, the bridge is the same bridge, but the load that you are putting on it is different. Do you have to always solve the problem from scratch and solve an equation as if you are looking at it for the first time? Or if it so happens that the load that you are putting on the bridge is showing up on the right-hand side, that A represents the bridge for you and B represents the load, and X is the response of your system to that external load. If all that you're changing is the load itself, do you have to redo everything from scratch? And the answer is no. And what comes to your rescue is the LU factorization. LU factorization says, okay, first time that you solve that system, you spend a lot of resources to solve it. But the second time around that you come and change the load on your bridge, you can get the answer to your system by a substantial saving in activities. If you have the LU recorded, you can use that information and see how to solve that equation much cheaper. So the answer to 1 is in cases where we solve AX equal to B for same A, but for many different B's, we can achieve substantial savings by using LU factorization. Okay, when you are solving one of these systems, the right hand side doesn't play much of a role. Is that right? On the left hand, you have some matrix times x is equal to right hand side. This is x, this is b, this is a. What do you do in Gaussian elimination? You try to get rid of all these elements. Is that right? And then you try to get rid of those elements. Well, regardless of what you got on the right hand side, on the left, you're always doing the same thing. All the way until your back substitution stage, everything is the same regardless of what you got on the right hand side. And essentially what LU factorization does, it just makes you aware of the fact that much of the effort that you have spent is a duplicate effort. From a one B to another B, you are doing exact same thing for zeroing out these elements and creating this echelon form on this side. So LU just makes that clear that is what is happening. And now let's go ahead do an example of solving AX equal to B using LU factorization and see. Excuse me. And let's see how does that come in handy. So item number 2, solving AX equal to B using LU factorization of A. Let me take an example. Here A is given as to us. So let me write it like this: 2x plus 4y minus 4z is equal to 12. X minus 4y plus 3z is equal to minus 21. And then minus 6x minus 9y plus 10z is equal to minus 24. Question is to solve this. And just so that the problem doesn't get to be loaded up with too many steps, typically the book comes in and helps you with the very first stage, so the problem becomes shorter. This is assume that 2, 4, minus 4, 1, minus 4, 3, minus 6, minus 9, 10 has the following LU factorization. So on the right hand side, so this is our A. This A is our coefficient matrix that you see here. And the book comes in and says, okay, I help you out. I tell you that if you do the first step of Gaussian elimination, these are the numbers you are going to get in the L. So this is your L, and what is left out of this is the U, which is 2, 4, minus 6, 5, 1/2. And we said the items we don't write, that means those guys are the way we want them to be, they are all 0. So we want to solve a system. This is really an AX equal to B. This is my A. The book says, okay, I'm going to help you by giving the LU factorization. So who is the B? Well, B is our right hand side. B is 12 minus 21 minus 24. Who is this? This is a record of what you need to do to make A to be echelon form. Who is U? U is what's going to be left out of A after you're done with that. Okay. Now how is that going to come in handy? Well, instead of solving AX equal to B, you really have LU. So here's my AX equal to B. Instead of A, I say, well, let's see, what can I get if I write LU X equal to B? On the face of it looks like it got worse. Now we have more things to worry about. But I come and say, let's break the job into two parts. It's very standard here. X is something I don't know, but L and U I know, whatever they are. For the moment, I go and say, well, this U time, if I don't know X, when I don't know U, what U times X going to be either. I'm going to call that Y. So this X that we are referring to here, this X that I'm writing, who is that X? X is vector of quantities you were after. Who are these? Little x, little y, little z. They are my ingredients of my unknown vectors. They are the capital X. So capital X is that little x, little y, little z. Okay, that matrix U times these unknown quantities is going to give me some other vector y, that is again capital Y. I can write it in capital. We are going to have a bit of a hard time with this. Who is y? Well, y is some other unknown quantities for the time being. We might call that, say, y1, y2, y3. Again, the challenge of linear algebra, keeping lots of little things in check, but the operations are very straightforward, just addition, multiplication, and such, keeping in mind who's who. Okay. So y is going to be some other unknown quantity. What becomes of my equation? My equation by now is L times y is equal to b. So who is L again? L is this lower triangular matrix. Who is y? Some other vector of unknown quantities. Who is b? B is my original right hand side. Whatever I got here, I still have it here too. What is the strategy? Strategy is solve this one first. So strategy is solve Ly equal to b first and get this vector y. Well, what do you do with that? Stage 2, well, what was y? Y was u times x. So by then you know what your y is, and then you say, well, your y came out of u times x. The original quantity where you were after was this x. You are saying u times x is equal to y, so you go ahead and solve this second time around. Okay, let's just go ahead and do it. Who is u? U is the upper triangular matrix that you have here. Okay, let's go step 2. I have my L. Let me copy my L. L times the vector y, which is some numbers. We still don't know what they are. That has to be b. Who is b? B is my right hand side. Let me write it here. Again, b was my 12 minus 21 minus 24. That's the original right hand side we had here. I just wrote it again. So right hand side that I have is this: 12 minus 21 minus 24. Well, is that a major challenge? As we write it out in the traditional format, we are going to see that solving this equation actually very easy. Let's just write it in the traditional format. I say 1, 0, 0 times y1, y2, y3. What is this? So y1 is equal to 12. Second step, what do I have? 1/2 y1 plus y2. What am I doing? I'm taking this row, multiplying by this column. What's going to be left when I do that? 1/2 y1 plus y2, no y3s, is equal to minus 21. Third row times this column, minus 3y1 minus 1/2 y2 plus y3 is equal to minus 24. Is that a hard thing to do? Well, what is y1? y1 already you have it, it's 12. How about y2? So I already have y1, I just plug it here and subtract. So what do I get for y2? Okay, negative 20, 27. Everybody sees what happened? Well, y1 is 12. You plug it here, becomes 6. 6, you take it, subtract it from that side, makes it minus 27. And then you go to y3. What do? You're just doing substitution here. Your y1 is 12, so this is minus 36, minus 1/2 of y2, so that is going to be plus 27 halves, and plus y3. That is supposed to be minus 24. So you go ahead and find out your y3 from here. This is minus 24. You add 36, subtract 27 halves. So that's going to be, you're saying what, 12 minus 27 halves. 24 minus 3 halves, if I'm not mistaken. Yes. Okay. Is that clear what we did? So we take our lower triangular matrix times a new vector of unknown quantities equal to the original right hand side that we had. We solve this thing and we see that the solution steps are quite painless, because step by step all that you are doing is that you're just doing substitutions. That's all you do. Okay, what do you do with these things? This y that we obtained here has the property that the upper triangular matrix that you had here times the original vector of unknown quantities is supposed to be these y's. So I go ahead and rewrite that. U times these x's is supposed to be these y's. So let's write it again. U was 2, 4, minus 4, minus 6, 5, 1/2 times the original. So let's remind ourselves, what are we doing? U times x is equal to y. This is my u. X are those things I was after from the beginning. Capital Y are these numbers I just got. So what step of Gaussian process is this going to be? Let's just write it out in the traditional format, see what is it. This equation is really 2x plus 4y minus 4z is equal to 12. And then minus 6y plus 5z is equal to minus 27. And 1/2 of z is equal to minus 3 halves. Well, how do you solve this kind of an equation? It's just a back substitution. So the other one using L was forward elimination. This is backward substitution. Essentially same thing. Again, you see it's a painless kind of an activity. So what is your z here? Negative 3. You go back up, you substitute in this stage, you say minus 6y that is minus 15 is equal to minus 27. So minus 6y becomes minus 12. So y becomes 2. Is that right? Make sure we are on the right track. And finally, we have here 2x. I have 4y, that is just an 8, minus 4z. That makes it, z was minus 3, so that's plus 12 is equal to 12. So what does that give me for x? So 12 and 12 cancel, I get negative 4. So the solution to the original equation, which was this, was obtained into 2 steps, rather painless steps, because everything was just done for me, because LU factorization was given to me. I have x is equal to minus 4, y is equal to 2, z is equal to minus 3. Compared to doing this thing from scratch, I have made substantial savings. Exactly what the savings are, we need to get into another issue of so-called operation counts. Like when you write a software code, you have to count how many times does this thing go through its activities. To compare 2 software versus each other, you have to do a test run, either theoretical or in practice, to see how much faster would one be compared to the others. For small systems, you don't notice the significance all that much. But if this was a system that was like 100 equations in 100 unknowns, small system as they come, the LU factorization is going to be about 30 times faster than the competition. Okay, so the speed up factor is really substantial, especially if your matrix is large. For large systems, there is really no comparison. LU beats doing things from scratch by a large factor. Essentially, that factor is the size of your matrix divided by 3. Like if your matrix was 3000 by 3000, LU would beat the competition by a factor of 1000 to 1. That's how much faster that is. That's how much you're saving. So it's not a big surprise, because the bulk of the work has been done here. The steps you go through Gaussian elimination are recorded here, and when you look at the steps that are carried out, you see that only the easy ones are left for you to do. That leads to the savings that you see. Okay, so this was the story for, let me repeat this thing again. It's kind of easy to get lost in the detail. It was A, our original matrix, times X is equal to some right-hand side. Say instead of A, suppose we already have calculated the LU. So it's LU X is equal to B. You have to have the large picture, so you are not drowned under little details. You know what's going on. Okay, U times X, temporarily we call it Y. So what we are left with is Ly equal to B. Now, Ly equal to B, that's the forward elimination step. It is like this stage. Solving it, just a matter of a bunch of substitutions, and you get the answer. Once you are done with this, so you solve, here's get B. Then you come back and say, well, Ux was called Y. Excuse me. Solve Ly equal to B and get your Y. Once you have the Y, bring it here and say, well, U times X was called Y. If you have Y, you have U, you can get X. You can solve Ux equal to Y and now get X, which was your original objective. So that is application of LU in solving standard equations of this style. So make sure you understand what is going on here. put it in front of you when you're solving example problems, and make sure it sinks in, and you'll be all set. Okay, the next object we were talking about, objective we had was, well, what if you have some permutations involved in your Gaussian elimination? What if you had to shuffle the rows? Well, why do you shuffle the rows anyway? If the pivot number is 0, you cannot use it. You have to shuffle it with a non-zero entry in the column that is there below that pivot number. In practice, even if the pivot number isn't 0, people do go ahead and do shuffling anyway, because that increases the stability of your numerical approach. That's a separate issue. So, at any rate, one way or another, perhaps you have shuffled your rows. What would you do then? Well, how did we say we shuffle 2 rows? Let's go to another page. Suppose you have a matrix like this. For whatever reason, you decide perhaps A was 0 and you have to bring one of these guys up and say I is not 0. If you want to shuffle row 3 with row 1, that act itself is said that's equivalent to a matrix multiplication. What matrix was it that if you multiply by this, will have the effect of exchanging row 1 with row 3? How do we create a matrix like that? You take the identity, and what do you do with it? Do exact same thing. So this row 3 will come here, and row 1 that was here will come here. So that is going to be one such matrix that will permute some rows for you. Suppose you go ahead and later on, for some reason, you need to exchange row 2 with row 4 of this guy on the final matrix. After you have done this, after you have done your elimination or whatever, maybe down the road you have to do one more shuffling. So by now you have this matrix. I wish I had written it on the right. So you had A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. You did one shuffle. Here's a record of that shuffle. Later on you want to do another shuffle. Just for the sake of argument, suppose whatever this thing is and the other stuff you have done, you want to exchange this with that. This is your whole matrix. You want to exchange row 3 with row 4. So again, you say, let me take an identity. I want to exchange row 3 and row 4 of this. So let's exchange them. Now, this was one elementary operation. You just exchanged 2 rows. This was another elementary operation. You again exchange just 2 rows. If you consider these two acts next to each other, what kind of a matrix are you going to get? Well, this is exchanging row 3 and row 4 of this one. So what kind of a matrix are you going to have? Let me fill it in so that this is going to 0, 0, 1, 0, 0, 1, 0, 0. Exchange these two. So 1 comes here, and this 1 comes down here. Okay? Now this is no longer an elementary permutation matrix. That is not the result of exchanging just 2 rows. Rather, it's result of 2 such things. So each of these things is called an elementary permutation. This is so-called general permutation matrix. Now imagine that you are shuffling a deck of cards. If you're very patient, you pull up one card here and one card there, and you exchange them, and then you pull up 2 other cards and you exchange exchange them, and if you were in one of these Western movies, probably by that time somebody's going to shoot you because you're just taking so long to shuffle all these cards. But any shuffling of a deck of cards can be done by shuffling just 2 cards at a time. If you had the patience, you could do it. But you could do shuffling any other way. You can throw up the cards up in the air, clean them up from the floor, and put them together. That's a shuffling also. There's a theorem that says any kind of a shuffling of a deck of cards is really a result of a sequence of shuffling of 2 cards at a time. That is, this kind of a general permutation is always a product of bunch of permutation of this. If you had the patience to do it, you can exchange 2 at a time until you get whatever shuffling you have. Now, this general permutation has a special look to it. Look at it for a moment and tell me what can you discover about the way the ones and zeros show up. If you want to give a description of such matrices, what kind of description comes to your mind? We want to have a matrix that captures the idea that we are practicing here. What is so special about the way zeros and ones show up in this matrix? For example, would such a thing be permutation matrix? No. What is it that you expect about the number of ones that show up in this? There is only one per row and a column. That's actually the definition of general permutation matrix. There is only one per row or column of a general permutation matrix. We are not explaining it in detail, but whatever that matrix, what it does, just shuffle things around, shuffle the rows just exactly the way you might shuffle the cards of a deck. Any such permutation matrix is a product of these elementary ones. Elementary ones only allow 2 cards to be exchanged at a time. Well, in any rate, suppose whatever exchanges you do, you accumulate all of them and write them under one matrix. That's what we are going to refer to as matrix P. So matrix P that we write is a result of all these permutations. So suppose you wanted to solve AX is equal to B. Say during solution stage you shuffle the rows around. The shuffling is equivalent to multiplying by a matrix. So I multiply both sides by that matrix. Now we have a little theorem that says if A is non-singular, you can go ahead and solve and get your root, then the matrix PA can be written uniquely as L times U. Okay, the matrix A, after you have done all the permutation that it needs to be done to it, P times A can be written as LU factorization that we have been talking about. Once that is the case, then you can go ahead and solve it like this. You say, okay, take the right hand side, apply your permutation to it. After you have shuffled this thing around, we go ahead and show this thing by B prime. So now solve LUX is equal to shuffled version of the right hand side, just the way we did at the beginning of the hour. Okay, so let me stop this thing and postpone the example of it for next time. We didn't have time for this thing. So what you want to do for Wednesday is to practice a few of the problems in this section, and I'll advise you to do the following from section 1.5, page 68. Do as many as it takes from these problems. Okay, choose a sub-selection of 9 through 16 at the minimum, whatever is on your assignment list, you do those. If you have problem, you do extra, and then I will explain on Wednesday what to do with the other problems.